Hello and welcome to Quiet 1102. Today we'll be discussing the command structure of the Quiet board, the basic command overview, and a few tips and tricks at the end. So let's get started. The command structure. The first byte in any packet to the Quiet board is a command, unless you want to break the code and have all sorts of random behavior from the Quiet board. This byte is broken into two nibbles, the higher being the command and the lower nibble being the command argument. This allows for up to 16 unique commands and 16 unique arguments for each command. As an example, the command could be read analog with the argument channel 1 and channel 3. The Quiet board would then respond with the analog value of channel 1 and 3. Not all commands have the argument implemented. An example of this is read digital. The command is typically written as hexadecimal to 0. However, since the argument isn't used, the 0 portion of the command is ignored, so you could also write the command 0x to A and it would work just fine. On the screen is a list of the currently available commands on the Quiet board. A full description of the commands can be found on the Quiet board website at the link in the video description. You should really check it out. It's pretty great. There's so many fun things on there. For this video, we'll be diving into the 4 basic commands: write to digital outputs, read digital inputs, write to analog outputs, and read analog inputs. First basic command, write digital. This command is typically written 0x to 0, or hexadecimal 20. After the command is given, the Quiet will take the next byte it receives and write it to the digital outputs. Boom! Nice, simple, complete, easy. As was mentioned with the digital read command, the argument is not used, so the lower nibble of the command byte is ignored. When features such as I2C or the additional PWMs are enabled, any bits in conflict with the data being written are masked off, or in other words, special functions have priority over the digital outputs. Read digital. The next command, 0x30, is a command to read the digital inputs. When this command is given, the Quiet will read the value of the digital inputs into 1 byte, because it is 1 byte of inputs, and place it into the output buffer. When the host device, or the computer, issues a read command from the buffer, this data will then be sent to the host. Nice, simple, no arguments. The first command in this video to use the argument is write PWM/analog. This command can be written as 0x42, meaning to write to analog channel 2, or 0x41, meaning to write to analog channel 1. When this command is given, the Quiet will take the next 10 bits received and apply them to the pulse width modulators with register. Because all data must be sent in bytes, 16 bits will be sent and the last 6 will be ignored after the command packet. The current Quiet firmware allows for up to 7 PWM channels. However, only 2 are enabled by default, so the remaining 5 must be enabled using the setting command. These 7 PWM channels can also be enabled in servo mode, but that is a discussion for another video. The last command we will be examining today is read analog. The command nibble for this is 0x5, and each bit of the argument specifies which analog channel to read. So, if the argument nibble was binary 0001, the analog conversion from channel 1 would be placed in the read buffer. If the argument nibble was binary 0100, then the analog conversion from channel 3 would be placed in the read buffer. And as a last example, and this is what I think is most exciting, if the argument nibble was binary 0101, both analog channel 1 and channel 3 would have their results placed into the read buffer. This argument style allows for one command, hexadecimal 0x5f, to read all analog inputs. Like the write analog command, though, only 10 bits of data are used, so a read from any channel will use the 10 most significant bits of the 2-byte response. And that's all the basic commands. Nice, simple, easy. If you want to learn more about other commands, or how to set up the additional PWMs or servo mode, feel free to visit the Quiet website in the video description as mentioned. The last few minutes of the video will be discussing a few tips and tricks to maximize the functionality of the quiet board. All of the examples for this presentation will be from National Instruments LabVIEW. The very first trick is in opening the port. The default setting of the VISA configuration serial port VI works very well, with 3 exceptions: the VISA resource name, enable termination character, and the timeout value. The default setting for timeout is 10 seconds, which is a really long time for a computer and can drive you crazy. When things are functioning correctly, this setting isn't a problem. But if the board becomes disconnected, or for some reason data becomes corrupted and stops flowing, your program will hang up for 10 seconds at each read node and will not respond. I will typically set the timeout to be less than 5 milliseconds. The reason behind this value will be discussed in a future video, but simply put, only one command can be given per millisecond. The next setting to change is the enable termination character. By default, the COM port will look for hexadecimal 0x0A as an incoming byte signaling an end of packet. This works really well in ASCII communications, but the quiet board communicates in a more binary style. Thus, the termination character will cause packets to be smaller than anticipated and cause your data to become misaligned and the buffer to overfill, reducing data throughput. Setting this input terminal to false will force the read function to read the number of bytes requested from the read buffer and prevent these unexpected read packet sizes. The final setting to change is the default resource name. This default doesn't work because there is no default. Haha, joke's on me. The easiest way to set this is to right-click on the pin and create a control. From there, navigate to the front panel of the project, open up the drop-down menu, and click Refresh. Open the drop-down again, and a few options should appear. Assuming that the quiet board is connected to your computer and the USB light on the quiet board is solid, it will appear as one of your COM ports. It will not be COM port 1 unless that is the only option. One final comment on the serial settings is about the baud rate. Because the quiet board acts as a virtual COM port and isn't a real COM port, the baud rate setting doesn't affect the rate that data will be transferred at. Because of USB protocol, only one data packet can be written every 1 millisecond to the quiet board. So, to maximize data throughput, make each packet or command string as long as possible. The example on this slide issues a command to read the digital inputs, write to the digital outputs, read all the analog inputs, and write to 2 of the analog outputs, all in one command. You could even have this expanded and write to all 7 available PWM outputs. This example code wasn't written for efficiency, but for readability. To increase the efficiency of this code, it would be better to write each command as a number instead of a hexadecimal string that is converted into a number. Some parts of this code that are very efficient, however, are the digital output writes and analog output writes. This function here is called bit array to number and is very effective at converting a series of Boolean buttons into a single number to be written to the digital outputs. This function here is a rotate function, so I'm taking an analog output with a range of 0 to 1023, rotating it 6 times to the left, placing it in the top 10 bits of 2 bytes. I then use the split function here to divide that into 2 separate bytes to send out to the quiet board. This method has been working very well for me and is the most efficient I have found to date. The right string in the previous slide will result in the digital inputs and all analog inputs being read back from the quiet board's buffer. This is the best way I have found to parse all the information from the read string. Here I convert the string into a byte array and delete the first element from the array, which pops it out that bottom piece into a sum all elements of array. Since there is only one element in this array, it is a very quick and easy function to turn the array into a single number. From there I run it into a number to Boolean array and then output it to 8 indicator lights inside of an array. On the front panel, the following 4 layers are just a copy of each other. But here I will take the next 2 bytes and delete them out from my byte array. This component here is called a typecast. This number here is in a U16 style, or unsigned 16, which is the format that the data is written in. I then rotate the value 6 times to the right so that the bits sit in the least significant locations. The rotate function is much more effective than a divide because it can be completed typically in a single command as opposed to over multiple command lengths. Here's the picture of the full example code used. A copy of this can be found on the QuietBoard website. Thank you for watching this video all the way through. If you liked it, throw up that like, show me your support. Share it with some of your classmates so that you're not the only one getting ahead, but we can all get ahead. And subscribe so that you can check out the next video that comes as soon as it drops. Thank you for watching.